everyone. Now here is a picture of the Telemecanique Altivar 28 power terminal board down here. Those are the main terminals. You have the line coming in and the motor coming out. The line comes in on R/L1, S/L2, T/L3, and the motor is connected to U/T1, V/T2, W/T3. PO is the plus bus from the three-phase bridge rectifier. PC is bus ground of the three-phase bridge rectifier. PA is connected to the pre-charge contactor, and PB is where you connect the regenerative braking resistor. That would be an external resistor there. The external resistor for the regenerative braking resistor is connected from PB to PA. Now there's a couple of things before we fire up this drive that we have to check. We want to make sure that there's no short circuits on the three-phase bridge, the regenerative braking IGBT or transistor, depending on your drive, and the IGBT or transistor output to the motor. We want to make sure, we have to absolutely make sure that there's no short circuits there. And we can do this from the terminal because we have the plus bus connection and the bus ground connection. If you didn't have that out here at the terminal, you'd have to pull the covers on the drive and get on the bus caps. So what we start out doing here on the main terminals of this drive, we want to put our black lead on plus bus and our red lead on L1, and we should have a good diode drop. Then we go to L2, another good diode drop, and L3, another good diode drop. And all of these diode drops here should be very, very close to in value. So for instance, we have 0.450 here, maybe 0.449, 0.50 here. All of these should be very similar. Now holding your black lead on plus bus, we go over to U, V, and W, and we do the same thing. We measure a diode drop there, a similar diode drop there, and a similar diode drop there. Now we go from bus ground and do the same thing. We diode drop L1, then we diode drop L2, then we diode drop L3, and all of those should be similar. Then we go to T1 and T2 and T3, U, V, and W, and you should have similar diode drops here. Now on this drive, there's a pre-charge contactor, and in the next diagram I'll show that to you. And there's a metal bar that connects plus bus off the three-phase bridge rectifier inside the drive to the pre-charge contactor on PA. And that's this little piece of metal, if you can see it in my picture right there. The next thing you want to check is to make sure that the regenerative braking transistor is not shorted. And that's as simple as going from bus ground to PB, where the regenerative braking resistor connects. It will connect from here, these two terminals connected by that metal bar, to PB. So you throw your meter across these two leads, and you want to check, make sure that it's not shorted. Hello everyone, we're back. Now what we have here is the simplified diagram of the input side, the line input side of the Altivar 28 inverter drive. Here's our three-phase bridge. Here's our pre-charge resistor, our pre-charge contactor, and our bus caps. Here is our R/L1 line input, S/L2, T/L3. Those are the line inputs to the three-phase bridge. Here is plus bus. Here's bus ground. Out here is our PO terminal. And here is our PC terminal. So to check the three-phase bridge for short circuits, we'll take our black lead, put it on the PO terminal, our red lead, put it on the R/L1 terminal, and we'll have a diode drop through this diode right here. Then we'll move our red lead, keeping our black lead over there on the PO terminal. Or we'll move our red lead to S/L2, and we'll have a diode drop through this diode right here. Then move our red lead to T/L3, and we'll have a good diode drop through this diode here. None of these diodes here should be shorted. Next, we want to check the diodes down here on the low side of the three-phase bridge. So put your red lead on the PC terminal, that's bus ground. Now put your black lead on R/L1, and we'll have a diode drop through this diode here. Move our black lead over to S/L2. We'll have a diode drop through this diode here. Then our black lead on T/L3, and we'll have a diode drop through here. Now the diode drops on the high side, on these three up here, will be just a skoshie bit higher, because we have to take into consideration that we're looking through the pre-charge resistor back through the diodes. So the pre-charge resistor comes into play here. If you can get your black lead over here on this side of the pre-charge resistor, all 6 diodes in the three-phase bridge should be very similar in value as far as diode drops go. You want to set your meter to diode mode when you do this test. Now the next thing in this circuit we want to look at is the pre-charge resistor. The purpose of the pre-charge resistor is to dampen the inrush current when we initially charge up the bus capacitors, these filter capacitors here. The filter capacitors in most inverter drives are huge, and when we first apply the line voltage to R, S, and T, L1, L2, and L3, we have a huge inrush current until those filter capacitors are fully charged up. So the engineers of these drives said we need to dampen that inrush current. So what they do is they put a pre-charge resistor in the circuit. So now we have a slower charge rate because of this pre-charge resistor right here. The pre-charge resistors value can be anywhere from 8 ohms up to 100 ohms. So when you put your meter across here, you should read a good pre-charge resistance. If you measure infinity ohms here, that means that the pre-charge resistor has opened up. Now, when the bus voltage here is at full charge, the processor is looking at the bus here, and it is waiting for a full charge across these capacitors right here. And when the processor sees a full charge across these capacitors, let's say for instance we have 460 line voltage, 3-phase coming in here. Our bus voltage is going to be about 650 volts DC right here. When the processor sees that there is 650 volts DC in our example here for a 460 volt line, it will close this contact right here, in effect taking out the pre-charge circuit in the circuit, bypassing that pre-charge circuit. So now all of your current is flowing through the contacts of the pre-charge contactor. The current takes the path of least resistance, and the least resistance being 0 ohms across the contacts. What happens, you'll see in some cases, the pre-charge resistor will open up. And that'll happen because the contacts here in the pre-charge contactor will fill up with sawdust. They'll pit from arcing, and so at some point you'll have very high contact resistance, and the contact resistance will be greater than the resistance of the pre-charge resistor. And we're running a motor drawing current from this circuit here, from the power circuit. Instead of going through the high contact resistance of the pre-charge contactor, now we pull all the current through the pre-charge resistor. And the pre-charge resistor will not last very long when you're pulling currents through it to run that motor. So if you measure an open pre-charge resistor, take a look at the contacts of the pre-charge contactor, and you'll find that you'll have a high contact resistance across these contacts here. Instead of 0 ohms when it's closed, you'll have a very high contact resistance. That's the line in circuit of an inverter drive. Not just our drive in particular, but you'll see this in servo drives, inverter drives of many types, servo drives of many types. The labeling will be different. For instance, out here you'll have R, S, and T, or you'll have L1, L2, and L3. Out here it'll say plus P, it'll say minus P down here for plus bus, minus bus ground. The labeling will be different on the terminals, but the basic structure right here will be very similar. Okay, in the next section we'll look at the motor side, the IGBT, the regenerative braking transistor, regenerative braking IGBT, and we'll go through that, how to test that. Hello again. In the last video we looked at the three-phase bridge, the pre-charge resistor, the pre-charge contactor, and the filter bus capacitors. This time we're going to look at the motor side. Here is the regenerative braking IGBT. Now on some drives it'll be an NPN power transistor. Now here we have an IGBT. Its collector is tied to the PB terminal. Over here we have the U/T1 terminal, and it is between these two IGBTs. This IGBT up here tied to the plus bus terminal PA. This IGBT down here tied to the bus ground terminal PC. Here we have the V/2 T2 terminal between these two IGBTs. And here's the W/T3 terminal between these two IGBTs. So in this drive, the Altivar 28, we have the regenerative braking IGBT and 6 IGBTs to run the motor. Up here we have the PA terminal, and that is connected by a metal bar. Put this diagram back in. That's connected by a metal bar back to plus bus on the PO terminal. So we have a metal bar that connects the PO terminal to the PA terminal. Down here is our bus ground. Now let's talk a little bit about the regenerative braking IGBT or transistor, depending on your inverter drive or servo motor. What is its purpose? Well, there are many cases where a motor will generate a voltage, and that voltage can become very high. It's called regeneration. So if, for instance, we rapidly stop that induction motor or that servo motor, or if, for instance, we have an elevator or a crane or somehow an inertia, a high inertia load, and we are letting that motor run very fast and running ahead of the actual PWM waveforms to the motor. Let's say, for instance, that motor is freewheeling, letting out a load, or trying to stop a high inertia mass. It's going to generate a voltage back onto the bus. So if, for instance, we have, in this case, a 650 volt DC bus right here, when that motor is rapidly stopping or running ahead of itself, generating a voltage basically, that voltage can become very high. And it can become very high very fast. This is our plus 650 volts DC. And that motor is regenerating back into the system. We don't want this voltage to become greater. Let me put this diagram back in here. We don't want that voltage to become greater than, say, these two bus capacitors right here. Let's say these bus capacitors were rated for 500 volts DC. And this one down here is rated for 500 volts DC. We cannot have a voltage greater than 1,000 volts from bus ground to bus plus. 500 plus 500 volts DC is 1,000 volts. But in some cases, especially during rapid deceleration, this voltage here can shoot way up to 1,000 volts or greater. And let's say it shoots up to 2,000 volts right there during our rapid deceleration of that motor, and it's regenerating voltage back into the bus here between bus ground and bus plus. Well, you don't want 2,000 volts across 5,000 volts of voltage value for these capacitors. You'll hurt those capacitors. This capacitor is rated for 500, that's rated for 500. You got 1,000 volts right here that you cannot exceed. But here we've shot up past 1,000 and we're hitting 2,000 volts. These guys right here will smoke. They'll smoke in a heartbeat. They're not rated for that voltage. They can't do it. And so what we have to do is clamp our bus voltage during regeneration of that motor to a safe level. Move this back out of the way. So here we've shot up to 2,000 volts up here. No, we can't do that. We can't do that. Those bus caps will not, those bus capacitors will not survive. So let's clamp our voltage at 750 volts DC. Okay, that's well below our value of 1,000 volts across those capacitors. Well, how do we do that? What we do is we tie, let's bring the bus back out here so I can connect to it. We tie a regenerative braking resistor right here to the collector of the regenerative braking IGBT or transistor. This is a high power resistor right here. It's low ohms also, it's not very much. So the processor is looking back at the bus. It's looking at this voltage right here. When the motor is regenerating voltage back into the system, this voltage shoots up to a value, and I just picked a value of 750 volts DC. It could be any value based on your drive. I've seen 750 volts DC, and that's why I picked that value. So here we are, we're shooting up to 750 volts DC of regeneration voltage. We start pulsing the gate of this IGBT or base if it's a transistor, and what that does is that connects the regenerative braking resistor to bus ground and clamps this rising voltage to a safe level. And the processor's still looking at the bus, and as we're clamping our voltage with this regenerative braking IGBT and this regenerative braking resistor, the voltage will come down, and the processor's looking at it and says, okay, are we back at 650 volts DC? Oh yeah, we are. Okay, well, let's stop driving the gate of the regenerative braking IGBT. This resistor right here, while it is in the braking mode up here, as it rises up above here, it'll be breaking at this point right here, above 750 volts DC. In our example, yours is going to be different. Your level of regeneration is going to be different. But when it's up above here, it is going to be dissipating that regenerative braking voltage. It will be dissipating this voltage right here into the atmosphere as heat until we get back down here to a safe bus voltage level, and then we stop the process of regenerative braking. Is that neat? That is neat. These people that make these drives, they're pretty smart. So how do we check this circuit right here? What you want to do, in our case, let's first check to make sure this is not shorted. Now, if your regenerative braking resistor, and you don't even need a meter to check this, but if this is smoked, charred, burnt, caught fire, that means that we're shorted right here, and we're pulling our 600 volts DC through the regenerative braking resistor, through our short circuit right here to bus ground. And this will open up in a heartbeat. You'll be able to smell it. We've seen some that were glowing cherry red before they opened up. So in resistance mode, put your meter across PA and PB, and you should measure a good resistance value of that regenerative braking resistor. It'll be written down on that resistor somewhere what that value is. So put your meter here on plus bus PA and on the collector of the regenerative braking IGBT, and you should measure that resistor value. If it's opened up, your meter will tell you. And if it is opened up, this guy right here, he's going to be shorted. So to check the regenerative braking IGBT or transistor, put your meter on PB and PC, and you should read open right here. If there's a freewheeling diode in here, like over here on the motor side as a diode, you'll measure that diode drop, but it won't be shorted. If it's shorted, this IGBT here is bad. So let's go over and measure the IGBTs for the motor. What you want to do is put your black lead on the PA terminal, put your red lead on U/T1, and you'll measure a good diode drop right here. If the IGBT is shorted, you'll measure the short. Now with your black lead still up here on PA, go to the V/T2 terminal. You'll measure the good diode drop. Don't want it to be shorted. W, put your red lead on W/T3 and the same thing. You don't want it to be shorted. You want to measure a good diode drop. All of these diode drops should measure very close to each other. Now that's the high side. We're going to check the low side IGBTs. So put your red lead on bus ground. That's the PC terminal right here in our case. Put your black lead on U/T1, and you should measure a good diode drop right here. You don't want it to be shorted. If it's shorted, you'll see it. It won't be a good diode drop. And now we go to the V/T2, with your red lead still over here on the bus ground terminal PC. We measure the good diode drop through here. If the IGBT is good, we'll measure that diode right there. If it's shorted, we'll measure from collector to emitter with a dead short or very low diode drop. Now let's go over to the W/T3 terminal and do the same thing with our red lead over here on the bus ground terminal. We'll measure through there. We'll measure through that diode right there. And we don't want to be measuring a short through any of these IGBTs. All 6 diode drops that you measure with this method, they should be very, very close to the same value. So for instance, if this one was 0.35, all of these other ones should be very similar in value to 0.35. If they're not, you need to go and find out why. So there you go. That's the motor side. This is the drive side of that inverter. It's very similar to servo drives, inverter drives. This example here being the Altivar 28, but this process here of running the motor with 6 IGBTs or 6 power transistors and regenerative braking IGBT or regenerative braking transistor, the regenerative braking resistor up here, those processes are a common occurrence in every drive that you will ever work on. Now sometimes this regenerative braking resistor here, instead of being external to the drive in our case, it will be internal. It will be built into the drive, mounted on a heat sink up underneath the drive itself. Isn't that amazing? That is amazing. There you go. That's how you test the motor side of an inverter or servo drive. Thank you very much for watching, and we'll see you next time.